Hi, I'm Filip Aronshtein,
And I'm Peter Weiss.
and this is our direct current source, our constant current source circuit. So we have a BJT over here. We have a potentiometer over here that's functioning as our RL. That's set to 0.5 kilo ohms. The middle pin is connected to VCC, which is set to 5 volts, and the bottom pin is connected to the top pin, the collector pin of the BJT. Now, that the BJT's bottom pin, the emitter pin, is connected to a 1 kilo ohm resistor, which is connected to ground, and then through the base pin of the BJT, we have two resistors connected over here in parallel of 47. Of parallel.
Yeah.
They're functioning as a voltage divider to take our VCC of 5 volts and turn that into 2.4 volts. We have a 47 kilo ohm and a 51 kilo ohm resistor.
Yeah, so the input into the base of the BJT is about 2.4 volts, and that's not changing because these resistances aren't changing. And the VE, the voltage at the emitter, is supposed to always be VB minus V gamma, so that always should be around 1.7 volts, the voltage at the emitter here.
So when we take that measurement, put this to ground, and then do the top pin, which is VC. Can you put it on the? We get 4.13 volts. But if we look at VE, the bottom pin, then we get 1.65, 1.66 volts, which is almost exactly 1.7, what we're looking for.
So this is our voltage amplifier circuit. Can I?
Yeah, here. I'll put it to ground.
So no, I'm not scoping anything. Just using it to point. So here's the BJT. To the collector of the BJT, we have RC, which is 2 kilo ohms, which I'm just using two 1 kilo ohm resistors in series, and that's connected to VCC. And to the emitter, we have a 1 kilo ohm, which is RE, and that's connected to VBB, which is minus 2 volts, which is this white wire here. And then the source VIN is connected to the base of the BJT here through this purple wire, and then we're scoping VB with this yellow wire, which is the same as VIN because they're directly connected, and we're scoping VC and VE are the two things that the outputs that we scope. So if we look at what we get when we do that, this is what happens when we scoped VB VIN, which is which is this yellow signal here, and VC, which is this blue signal here. So there's a DC offset of around 2.4, which is an artifact of the fact that VCC, VEE, and V gamma are all not 0 volts. So the offset comes from those voltages. VE is not ground, V gamma is not 0 volts. There's like 0.7 volts. So that's where the offset comes from. It ends up being around 2.4 volts. There's a gain of about 2. The amplitude of this blue signal, VC, is about twice the amplitude of VIN, and we can look at that here. We see the amplitude of VIN is around 250 millivolts, and the amplitude of VC is around 500 millivolts or 0.5 volts, because the peak to peak is around 1 volt. The peak to peak here is around 0.5 volts. So the gain is about 2, and you can look and see that this is VC is actually inverted from VIN2 because this starts going down, this starts going up. So it's an inverting amplifier that with a gain of around 2, and that matches up with this the frequency response. So inverting, the phase is around 180. At high frequencies it starts doing weird stuff, but at low enough frequencies the phase shift is about 180, so it's inverted, and the gain is around like 5 decibels, which is about what 2 is, not in decibels, if we look at the frequency response for VC compared to VN. Okay, and that is our lab. Thank you.